These are the notes for LT1 in the Earth and Space Science unit. And target says I can calculate how the weight of objects vary. Vary means change, depending on the planet or really any place they are located outside of the Earth. It could be on an asteroid, within a star, whatever. Alright, so just predicting how weight would change based on where they are at, assuming that's outside of the planet Earth. Alright, something to think about. If you were to travel to Mars, would your weight or mass change? Kind of just make a mental prediction here. Would they both change, or would neither change? Alright, so kind of stop and think. Just take a guess on that. 6th grade is where you typically talk a little bit of physical science concepts. And in 6th grade, you should have talked about this concept of mass. Alright, and if you were to Google it, it would talk about the amount of matter in an object. That's technically an object's mass. Right? So whatever makes up an object. So if we were to look at a human body, right, think about the tissues within the human body. There's bone tissue, there's skin tissue, there's organ tissue, there's hair. Okay, so all of those types of tissues make up our mass. All right, so now kind of go back and rethink this. Perhaps you had a mistake. Would your mass change just because you hop on SpaceX and travel to Mars? Okay, it probably, I would think it would not, unless you eat really well on that thing and gain weight, or you don't eat and lose weight, lose mass, I should say, not use those two interchangeably. Nothing about your mass is going to change. So mass does not vary based on location. So if you were able to travel to our moon and walk on the moon, your mass doesn't change. It's the same as it is as you were sitting here taking these notes. When you see practice problems here, eventually, when we are calculating the weight of an object, you'll be given a mass, and the mass will be in grams or kilograms. Okay, so when you see something in grams or kilograms, realize that we're talking about mass in those situations. Which leads us to this weight idea. So weight. Weight is a result of gravity's pull on an object's mass. Alright, so we know that if you step on a scale, it gives you your weight. It is not measuring your mass. It's not measuring the amount of stuff in you. It is measuring how hard is Earth pulling down, which is causing you to compress a spring within your scale, and that is putting a reading on the screen. Alright, so you're actually measuring gravity's pull on your mass. Now I know we in the United States, we have our own way of doing things. We decided to measure weight in pounds, but in science it's more of a universal language. You're going to see weight given in newtons, which hopefully will make sense, because back in Physical Science A, we talked about, when you had the force of gravity being down, okay, that was newtons. That's really measuring your weight now. Okay, we didn't take it that far, but your weight is just a force of gravity on you. So this is going to change. Okay, if you're in class, we go through a mass versus weight gizmo. And it's not a packet you have to do, but it is on your list. So you go to explorelearning.com, you'll see like a little dog and some objects, and it's mass versus weight. I encourage you to play around with that, because that really helps to put some of this stuff in perspective. One of the major topics we have to get, other than knowing the difference between these two, we have to know that mass and weight are directly proportional. Mass and weight are directly proportional. So, if you have more mass, I can tell you after the holidays, I add a little bit of mass to my body. And therefore, because I add that mass to my body, when I hop on the bathroom scale, I'm usually too scared so I don't, but if I hop on the bathroom scale, I'll see that my weight also went up. Okay? It won't go up at the same rate. I might have added 500 grams to my body. That doesn't mean I'm going to go up by 500 pounds. Or anything like that. So don't feel like that's going to be the same number, but more mass, you're going to have more weight. Similarly, if I run a little extra and eat a little less, my mass will go down a little bit. that would register as less weight on the scale. Earth isn't going to pull on me as much here as it does up here. Okay, so mass and weight are directly proportional. So you'll be able to play around like with a, I don't know, it's like a watermelon and a baseball and a dog and whatever, and you'll see the more mass they have, and then you put them on there's a spring scale, you'll see that you get more weight in newtons. It also allows you, there's a little drop-down menu, to play around with astronomical, this is a big word, so think astronomy outside of the Earth, astronomical body size. So what that would be, maybe you're on an asteroid, maybe you're on a moon, maybe you're on Jupiter, okay, where are you? So astronomical body size and weight are also directly proportional. Okay, so they are also directly proportional. So if you were to have a dog, you have a little dog character on that gizmo, and you put the dog on the moon, which is very small, versus Jupiter, if that was possible. It's a gas giant, so that would not be good for the dog. But if you were to put that dog in those two locations, you would see that the moon, because it has less size, okay, let's say the moon here, you would see the dog would weigh less. Okay. We put that same dog, but we put it on Jupiter. So let's take it to Jupiter, and now all of a sudden the dog has more weight. But if you look, it's the same little foo-foo dog, like nothing changed about the dog, so mass has no relationship to this. Okay, but because the size of the planet, the astronomical body, whatever, because that changed, big objects like Jupiter pull harder. The sun pulls far harder on Earth than we can pull back. All right, so just kind of think about that. Maybe pause it here and let that sink in. I encourage you to play with that gizmo. All right. I feel like these are on Moodle, a copy of them, but if not, you can probably see it on here. You could get a copy from me in class, email me, I can send it through to you, whatever the case might be. But the math for this target is very simple. Okay, it's a simple formula, and you'll find it on your formula sheet to calculate weight. It's mass times gravity. Gravity, we round it to 10. Okay, we talked about that in physical science A. It's actually an acceleration, but if an object falls for 1 second on Earth, it'll be going 10 meters per second. If it falls for 2 seconds, it'd be going 20, 30, 40, all the way up. All right, so it doesn't mean you ever have to square the 10. It just means gravity pulls 10 meters per second faster every second. So if you get one of these super simple problems, like number 1, it says calculate the weight of a 40 kilogram object on Earth. Okay. We have a mass, and we see 40 kilograms, and we know that is a mass. We know the gravity on Earth is going to be 10. So therefore, our weight is mass times gravity. So it's going to be 40 multiplied by 10, which is 400 newtons. Okay, simple as that. Okay, so if I give you the mass of something on Earth and you need to calculate weight, it's just that mass multiplied by 10. Number 2 on your practice problems says calculate the weight of a 40 kilogram object on an asteroid where gravity is 3. We no longer use that 10 of Earth for anything because we're not on the Earth anymore. We've landed on an asteroid. And so for number 2, the formula is the same. It's mass times gravity, but the gravity on the asteroid is 3. So this time, the weight is the mass multiplied by 3, so 120 newtons. So the weight of that same 40 kilogram object, just by taking it to an asteroid that is smaller, you can see its weight changed, mass would not. The third type of question you'll see is like number 3. And number 3 says calculate the weight of that. Let's just say it's the same 40 kilogram object. You're going to go to planet X, just some make-believe place, whose gravity is 3 times that of Earth's. So think about that. If we know Earth's gravity is 10, and something is 3 times that, we would need to multiply those together. So this type of problem takes one extra step. It's still not super complicated. All right, so we need to find the gravity on planet X. And to do that, it's going to be Earth's gravity, which is 10, multiplied by 3. So the gravity on planet X is 30 meters per second squared. And now that you know that, same process. Weight is the mass. I said it was still 40 kilograms. And now you're going to planet X, which has a very strong gravitational field, so it must be a really big planet. And so 40 multiplied by 30 is 1,200 newtons. Okay, 1,200. The answer key to this is on Moodle, so I'm not going to go through every single one of these. But if you look at 4 and 5, same process as number 3. Gravity is 0.25 times that of Earth's. We would multiply 10 multiplied by 0.25, which is 2.5. And then 2.5 multiplied by 40. What is that, 100, I think? 100 newtons, something like that. So same process right there. When you get to number 6, I've given you gravity. So this would be just like number 2. Okay, number 2, where you were given a different gravitational field. 7, just like question number 1. We're back on Earth, so we use 10. Number 8, pay attention to the questions. It says calculate the mass. Stop and think about that right there. Mass doesn't change. Here's the mass of the pumpkin. That pumpkin could be on Earth, it could be on the moon, it could be on planet K. I don't know what that is, but whatever. All right, doesn't matter where it is. The mass doesn't change. So don't let me trick you. You would just type a 6 into Moodle for this one. All right, and that is target 1. Good luck.